This video is an introduction to the Milky Way Galaxy. We'll talk about some of the makeup of the galaxy, basic shape, and get some understanding of how dust in the Milky Way Galaxy greatly affects our observations. So just sort of a definition of galaxy, these are common objects in our universe. And we'll be studying them in a series of videos here, and they'll be important as we talk about cosmology in a future unit. But we talk about gravity here, giving us the organization of stars, gas, and dust, and there's going to be more to the story than just the gravity from stars, gas, and dust. We live in the Milky Way Galaxy. Our sun is a little bit in the suburbs of the Milky Way Galaxy, not towards the center. But we're definitely a member of the Milky Way Galaxy, and no one's counted, obviously, all the galaxies that are in the universe. We can't see them all, but a guess would be 100 billion galaxies in the universe, and sort of an educated guess by sampling different areas of the sky. So some questions we would be concerned about. We live in the Milky Way Galaxy. What's that mean? What's the shape of the Milky Way Galaxy? What's its size? What's its organization? What's it made of? What components are in the Milky Way Galaxy? And we're going to answer a question in this video about how we can learn about the galaxy and visible light. And in a future video, we'll talk about radio astronomy, exploration of the Milky Way Galaxy and infrared. But you look out the sky, you see the band of the Milky Way. If you don't live in a city, if you live out in the country, you can see that band of stars in the summer and also in the winter, going past Orion, above Orion. So here we go. 1785, Herschel, with his sister, the good amateur astronomers, made a map of the stars they saw in the sky, and there was a tendency for the stars to kind of cluster in a band around the sky. And what they did was put the Earth here and then map out the counts of stars in different directions around the sky, and they came to the conclusion that we were kind of in the middle of a flat arrangement of stars. So using visible light, just their eyes through a telescope. No photography existed at this point, but doing star counts around the sky, very a little bit, let's say, tedious procedure, but it was accomplished. They came up with a map that you could call this our galaxy, knowledge of our galaxy in 1785. This is not the Milky Way Galaxy. We can't take a photograph of the Milky Way Galaxy because we're inside it, roughly about that distance away from the center. This is not quite the right shape for the Milky Way Galaxy, but it's vaguely similar to it. But in the Milky Way Galaxy, we've got stars, we have gas and dust, and then there's some strange stuff we'll not talk about in this video called dark matter that has gravity but does not emit light. So investigating the Milky Way Galaxy, one investigation concerned the diameters of open clusters of stars. These are clusters that are in the plane of the Milky Way Galaxy, in that band of light across the sky that we call the Milky Way. So these open clusters, the diameter was measured, and then by the brightness of the stars, the distance to the cluster was determined. And we see here a relationship. This is distance away from the sun, and don't need to know what the numbers are, but the distance is increasing off to the right. In 1930, Trumpler came up with this graph, and diameter increasing vertically here. I'll tell you what the graph is saying here. It's saying that if a cluster is close to the Earth, it's kind of small. If the cluster is a medium distance from the Earth, it's a medium-sized cluster. And if a cluster is far from the Earth, then it's a large cluster. So that's kind of interesting. What's your conclusion from that? Do you think the sun or the earth controls the size of these clusters of stars? It would be a few hundred stars perhaps in an open cluster. Do you think the sun somehow influences the true size of these clusters? And no, the sun does not influence the size. There's a problem here. That problem is that there is a significant amount of dust, not an overwhelming amount, but a significant amount of dust that blocks starlight. It dims starlight and also reddens the starlight. We'll get to that. But dims the starlight. So if the cluster is a long distance away, there's going to be more of this dust between us and the cluster, and the star's light dims down more. Dim objects are treated as farther away in astronomy. So before they knew about the presence of the dust, and before they could correct for it, they saw these clusters with dim stars. They were thought to be far away. The angle in the telescope of these clusters can be measured, and you can calculate then the true size of the cluster just by measuring the distance, by multiplying the distance to the cluster by the angular size of the cluster. The problem here is that the distance numbers are wrong due to the effect of dust. The dust was making the stars too dim. That was making the stars too far away, the cluster too far away, and that made the calculation of the size too large. So around 1930 here, Trumpler gives astronomers an idea that there's a problem in our interpretation in looking at stars. There is a medium in between stars, gas and dust in between the stars. So again, this graph said that there was a relationship, a correlation between the size of a cluster of stars and the distance from the sun or the earth. That's unreasonable to think that the sun is in a special spot in our galaxy where further away from the sun things get bigger. So it's not true. And Trumpler came to the conclusion that something was dimming the starlight. Dust was dimming the starlight. And that had caused him to miscalculate the diameters of the clusters. Well, this interstellar medium, the dust is one element of it that has an effect on our observations. And there's gas in the interstellar medium as well, hydrogen, helium. But the interstellar medium is just sort of incomprehensibly thin with very little material. There's a lot of space in the Milky Way Galaxy, so even though there's not a lot of material in each cubic meter, there's a lot of cubic meters in our galaxy, and it's an order of 10% of the mass. So the other 90% would be stars, basically. And we have a situation here where it's not an ignorable amount of material in between the stars. So measurements have been made of the material. Most of it's gas, most in the gas form, hydrogen and helium, and then 1% dust. And it's fortunate for us that it's not more dusty than this. This dust limits our vision as to how far away from the sun we can view stars in visible wavelengths. So how thin is the interstellar medium? And this slide comes from a Hubble telescope presentation. We have things on the Earth here, liquid water, the Earth's atmosphere, on a vacuum cleaner. It pumps out air from its system. Inside a light bulb, it's not empty space. There's still 10 to the 14th particles per cubic centimeter inside the light bulb. In a special laboratory, pumps can remove particles from a chamber, but still 100,000, 10 to the 5th, 100,000 particles per cubic centimeter. where the stars form, these giant molecular clouds, they don't start off as dense objects at all, better than the best vacuum on the Earth. Then we start to get to the in between the stars, roughly 1 particle per cubic centimeter. 1 particle per cubic centimeter. And it's, there are 2.5 centimeters in an inch. So we're talking about something smaller than a cubic inch, but only 1 particle. And then in between the galaxies, we'll do more on that when we talk about galaxies, but you need 10 to the 5th cubic centimeters to find 1 particle. So we have a situation with the space between the stars pretty empty. There's not much material here at all. But it has noticeable effects, because in the vast volumes, this little material in each cubic centimeter becomes effective at distorting starlight. And what do we mean by dust? So dust particles of atoms collecting together, they can form in the atmospheres of the red giants or form in the space between the stars. And they do 2 actions on the light. They have interstellar extinction. So if you would throw up a cloud of dust between you and someone you're looking at, it would be a little bit more difficult to see the person. Dust storms that roll across the southwest United States or in California sometimes make traveling hazardous on highways. They limit the view of the drivers. So that's one thing, interstellar extinction. Extinction in the astronomy sense just means dimming the light. Dimming the light. So starlight scatters from that beam. And then if you recall, red sunsets, it's not all due to dust in our atmosphere, but basically this happens to starlight. As the starlight passes through the dusty regions, the blue wavelengths scatter more effectively than the red wavelengths. So red tends to make it on through. So we get a change in the proportion of intensity in the colors of light. More red light makes it through, less blue, and the stars become reddish, tinged reddish. Let's say they don't change totally to red stars, but they lose some of their blue light, and the red light more easily makes it on through. If you might recall, color is somewhat related to temperature, and we talked about hot blue stars and cool red stars. Astronomers can still tell the temperature of a star, of course, by looking at the absorption lines of the star. They don't rely on just the overall color to determine the temperature. So here's a little summary again. Dust has these 2 effects. We're not talking about gas now, we're talking about dust. Dust dims the light, and it dims it out such that we can only see stars in our galaxy that are closer than 6,000 light years. This is a little bit of a problem with using visible light, because it's 27,000 light years to the center of the galaxy. We cannot see with visible light the center of the galaxy. We can with infrared, but not with visible light. We're limited. Dust dims the starlight too much. Then the other thing, the reddening effect here, the blue light is scattered from the starlight beams that are coming towards us more than the red. But again, studying the spectral absorption lines allow astronomers to calculate the temperature of the star. So as far as the gas, the light basically passes through the gas unless the wavelength of the light matches some transition energy gap for electrons in the gas. And when that occurs, there can be absorption lines in the spectrum of the star. So if you recall the spectroscopic binary stars, where the Doppler shift shifts the absorption lines back and forth as the stars orbit each other, move towards us, move away from us, those lines will shift back and forth. In studying the spectra, astronomers can see some lines that are stationary. So we have the absorption lines for the 2 stars moving back and forth as they orbit each other and alternately come towards us and move away. But then there are some absorption lines that stay fixed. But what creates the fixed absorption lines? Well, they're not moving with the star. It's not created by the star. Instead, it's the interstellar gas that does not have this bulk motion of any notable speed. And it's not alternating. The gas in the galaxy doesn't move towards us and then move away from us, slosh back and forth. But astronomers can detect these absorption lines, determine what element is there, and determine what percentage composition the interstellar medium is, hydrogen and helium. So here's a photograph in visible light, what we can see from the Milky Way. And there's more indication here that there's dust in thicker concentrations. These dark bands are blocking the more distant starlight. And here's towards the center of our galaxy. This is a view from the southern hemisphere. We get a little better view of the Milky Way Galaxy. So I'd ask you to write down some questions. That's where this video is going to end. Astronomers tried to map out the shape of the Milky Way Galaxy in the 1700s, and they did map the sky and do those star counts, but they were misled because they did not realize the effect of dust, limiting how far we can see with visible light. So we have more gas than dust in the interstellar medium. The dust has the major effect, though, on the starlight of dimming it and making it redder. The gas between the stars just puts a little bit more absorption lines. They're not major absorption lines in the star spectrum, but puts some absorption lines in the star spectrum. So there's our introduction to the Milky Way. Keep reading and asking questions.